Welcome back. This is confidence intervals for means where we do not know the population standard deviation. In this section, we're going to present methods for finding a confidence interval when the population standard deviation is not known. With sigma, which is the population standard deviation, is unknown, we use the student t distribution. Instead of a normal distribution. When finding a confidence interval for mu, the population mean. The student t distribution was developed by William Gosset from 1876 to 1937. He was a famous Guinness Brewery employee. He needed a distribution that could be used with small samples. The brewery where he worked did not allow publication of research results, so he published under the pseudonym Student. So he didn't use his real name. In real circumstances, we don't usually know sigma, so sigma is typically unknown, which makes the methods of this section realistic and practical. And if you notice, we're not even going over when we do know the population standard deviation, because it's more times than not that we just don't know it. So it's better for us to just study this one. So let's talk about a little bit about the student distribution, the t distribution. You can see it down here, and it looks like a normal distribution, which it kind of looks like a normal distribution because it is symmetric, but it's different. The t distribution is different for different sample sizes. N. So if I have a bigger N or a smaller N, it's going to make a difference. It's still going to have that symmetric bell shape as the normal distribution, but it does reflect greater variability, which means that it's wider than the standard normal. This gives us more room for error. This t distribution also has a mean of 0, just like the normal one when we did proportions. And the standard deviation varies with sample size. It decreases as n gets larger and is greater than 1. So the standard deviation, the curve will get a little bit skinnier. It won't be as wide as n gets larger. As the sample size increases, the t distribution looks more and more like that standard normal. So down here, if we look down here on this, we see that the blue one is the standard normal. The student distribution, t distribution, when n equals 3, say how it's shorter, and it's going to be more wider. So see how it's wider down here. So it's going to go a little bit further down when we get closer down to the bottom here. So it varies a little bit in shape, but not a whole lot of difference in terms of shape. Just like when we did the proportions, we have this curve. It's going to look different. It's going to look kind of the same, but we're going to know in our head that it's a t and not a z. So z is for the normal distribution, and this time we're doing a t distribution, but it looks pretty much the same. And we still have that middle, which is going to be our point estimate, which in this case is our sample average. And then our confidence interval is going to go from here to here. And then I have the area down here. Let's go ahead and look down here at number 5. You are 99% confident that the true mean of number of hours that a college student watches per day is between 2.3 hours and 5.89 hours. Find the point estimate and the margin of error. Draw a picture representing these values on the graph above. I'm actually going to have you do it down here, because I probably wouldn't give you a picture again like I did for the proportion. So we're going to draw our t distribution. So this is a t. I know it's a t because I'm talking about means. And I'm going from 2.31 to 5.89. So if I'm going from here, which is 2.31 hours, to 5.89 hours, and this is 99% confident, then I want to know what the point estimate, which means I want the sample mean, which for us is x bar, and the margin of error. Just like when we saw in the previous videos where we saw for the proportion, the middle here is going to be my x bar. And I'm going to get it by finding the average of these two. So my x bar is going to be 2.31 plus 5.89 over 2. Go ahead and do that on your calculator. You should be getting 4.1 hours. So that was our sample average that we found when we said how many hours of TV a college student is watching per day. And if I wanted the margin of error, so this is my point estimate, is that 4.1 hours. And if I want the margin of error, if you remember from a previous video, then I can either find it by subtracting these two numbers or by adding subtracting these two and dividing by 2. So my margin of error is going to be 5.89 minus 2.31 divided by 2. And you should be getting 1.79 as my margin of error. You can also find it by subtracting these two or subtracting these two. All of them should be giving me around the same number. And I would accept any of those ways to find that margin of error as long as you're showing me the proper work. Because we said that n matters, how big our sample size matters, we need to discuss the number of degrees of freedom. The degrees of freedom is the number of values in the final calculation of a statistic that are free to vary, and we shorthand by saying DF, degrees of freedom. Now let's talk about what this means. Consider the game of baseball. We understand that the field of play consists of 9 positions. The coach is free to assign any of those 9 players to the 9 positions. But once that 8th player is assigned, the 9th player is kind of set. So if I have n equals 9 players that are going to be on the field, then I can choose who I want for first, and I have a choice for second. I have less choices for third, but I still have a choice, and so on. So I have choices for those first 8. But the last picked is no choice. This means that I have a degree of freedom of 8 because I had some sort of freedom to choose for those first 8, and that last one's chosen for me. If I have a random sample of 16 light bulbs produced in a larger batch is selected and the mean of sample hours is 1,450 and the estimated standard deviation is 80 hours, what's the degree of freedom? Remember, degrees of freedom doesn't matter about standard deviation and the sample and everything. I'm only looking at how many there are. And so, again, just like when we saw with the last one, for the first 15, we have some freedom of choice. Even on that 15th one, I have a few to choose from, but that 16th one, I don't have any choice, and that's why my degrees of freedom is going to be 15. You observe height and weight in 100 subjects. You have 100 pairs of observations since each observation of height and weight constitutes a pair. If you want to calculate the correlation for these two variables, your degrees of freedom would be, now this time is a little different since it's pairs. When I make my first choice, it's height and weight. And then I make my second choice and my third choice. So I have, since I'm choosing pairs, how many am I going to have left that at that last choice? When I make that last choice, I have to choose the last height and weight. So my degrees of freedom are going to be 98 because I have 100, but I don't have a choice for those last 2 because it's height and weight coming together as a pair. Now, most of the time, our degrees of freedom is going to be n minus 1. And for us, it's always going to be n minus 1 in this section. When we don't know the population standard deviation, we're going to be using t as our critical value. Before, we were doing z alpha over 2, and this time we're doing a t alpha over 2. Our confidence level is 99%, so that's going to go in the middle. This gives me an alpha of 0.01. So I'm going to say 0.01 is left over, but I have to split it up. This area is going to be 0.01 over 2. So my alpha over 2 is going to be 0.005. So this area is 0.005, and this area is 0.005, so that all together it's adding up to 1, or 100%. Now, just like before when we did proportions, I want this critical value right here. And before we did inverse norm. And this time we're going to be doing inverse t. And for inverse t, it's going to be area to the left, comma, degrees of freedom. Let's go to our calculator and see how we do this. All right, so in here I'm going to go to second vars to the distribution. Here's inverse norm. This is what we would be using if we were doing a z distribution or the normal distribution, but we're not. And so we have inverse t down here. I'm going to hit enter. And I'm going to say area to the left. Now, if I was finding that left critical value, it was 0.005. Comma, there was an n equals 29, so my degrees of freedom is 28. I'm expecting a negative number because I have this negative 2 point because I was on that left side. If I were to do the other side, it would be 0.99 plus that 0.005, which is 0.995, comma 28 again. And notice I get the exact same thing but the positive version, and that's what we were expecting. All right, so let's go back to this. So my inverse t, area to the left, degrees of freedom, was inverse t. Area to the left was 0.005. Degrees of freedom was 28. And we got a negative 2.76. And technically, my two critical values are plus and minus 2.76. And if you don't have, some of you may not have the higher versions of the TI-83. If you don't have the plus version, you may not have that inverse t. This means you're going to have to either borrow one of my calculators in class or from a classmate, or you will have to use the tables. And I'm not going to go over the tables in the video, but you're welcome to see me after class or in office hours to go over how to use those if you do not have that inverse t. Once again, we're going to be using panic because we're going to be doing confidence intervals. Only difference now is we're going to be doing it on means. So just as before, P stands for state your parameter. If you remember when we did proportions, we said P equals the true proportion, blah, da, 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 da. Now we're doing means, so it's going to be mu equals the true mean of whatever we're trying to find. State and justify your assumptions. Name your interval. I is find your interval. And then write a conclusion in context of the problem. So just like before when we did it with proportions, I'm going to be able to look at your conclusion and know exactly what the question was talking about. The assumptions that we're going to use is that it's an SRS, or if it just says it's random sample, that's fine. And for part 2, either the population is normally distributed or n is greater than 30. If n is not greater than 30, you need to check the data to see if it's approximately normal, such as a histogram or box plot, to make sure. I might also say, assume that the assumptions have been met. And that's what you would say that it says to assume that they're met. All right, so let's do an example. An archaeologist discovers a new but extinct species of miniature horse. The only 7 known samples show shoulder heights in centimeters of these figures listed. Find the 99% confidence interval for mu, the mean height of the entire population of ancient horses. Assume all assumptions have been met. So let's start. I know I'm doing a confidence interval. I see that it's means and mu. I have a 99%. I have this data here. This data I'm going to plug into L1. Let's go ahead and start by doing that part, and then we'll go back and we'll do all these here. So let's go to our calculator. All right, on our calculator, you should be saying stat, edit, and I've already punched these into my L1, but go ahead and make sure that you've done the same. Pause this video if you need to. Once you have them punched in, let's go ahead and go to stat. Oops, I pushed second by accident. Stat to test. And we're going down to t interval. So before we did 1 prop z int, which was down here, this time we're doing t interval because we're doing a t distribution and we're doing a confidence interval. So let's go here. If I had stats to plug in, I would go over here and push stats, and you can see all the stuff that I'd have to plug in. I'm going to go to data because I actually punched in data. And down here, if you had something else here, then like L2, you can just clear it out and push second L1 to plug it back in. Frequency should always be 1 for these. And then my confidence level was a 99%, and let's hit calculate. So this is going to be in part of our panic, so I'm going to come back to this and write this down when we do the full-blown panic. Let's go back to our notes. All right, we're ready to do our full-blown panic now. So our P, this time I'm doing the mean, so I'm going to say mu equals the true mean height in centimeters of all ancient horses. Our A, we only had a few, right? There's only seven data points. It's definitely less than 30, and it doesn't say random because it said these are the only ones, but it does say to assume all assumptions have been met. So even though it's not following the rules there, it does say all assumptions have been met. So we're just going to write that down. Says assumptions met. And you just need to write that down and check that off if I say that. Our N, we had gone to t interval on our calculator. The actual interval was 44.475 to 47.81. And our conclusion is going to look very similar to what we did when we did proportions. We're going to say we are 99% confident that the true mean height of all ancient horses is between, and I'm going back to this, 44 point, and if you round off a little bit, that's okay here, between 44.8 centimeters and 47.8 centimeters. Keep in mind, just like before, I should see the 99% confident. I should see the true mean or the true proportion or the true whatever you're looking for. It's got to address what it's talking about. Now, since we're talking about means, you should have some sort of label now. Before we didn't because we were saying proportions, like percents. But this time we should have centimeters or dollars or whatever it is we're talking about. So there should be a label on these. We are trying to find the average time for an installation of a certain hardware. A computer technician installs his hardware on 64 different random computers with an average installation time of 42 minutes and a standard deviation of 5 minutes. Compute a 95% confidence interval for the mean installation time. All right, so a few things here. I'm seeing the 94% or the 64 random computers. I see an average of 42 minutes, standard deviation of 5, 95% confidence interval. I know that I'm doing a panic. I have the information here. Let's go to our calculators first, get our information, and then we'll start running through all of the steps for panic. All right, so now we're on stat calc. I'm trying to get to t interval. which is number 8. You could also just push 8 to get to that, and you'll still see at the top here that you're in the right spot. Last time we did data, this time we're doing stats. They didn't give us data this time. Our X bar was the average. I had an average installation time of 42 minutes with a standard deviation of 5 minutes. And the N was 64, and we wanted the 95, so 0.95 confidence interval. Let's make sure we plugged in everything correctly. And let's hit calculate. All right, so I have this here. I'm going to use this again when I go back to here, but let's go ahead and go back to our notes and run our panic. All right, so let's run our panic here. Our P, our parameter, this time since we're doing mean, it's a mu. Mu equals the true mean, or you can say average, time for installing. It doesn't say what this hardware is, but we're just going to say for installing the hardware. A, it doesn't say to assume everything's correct, so let's go ahead and run through. It does say, does it say random? Random, here it is. So on 64 different random computers, so we're going to say says random. Check. And the other thing when we're doing means, our N has to be bigger than 30. So our N is 64 greater than or equal to 30. That checks out as well. If you don't give me these numbers or say that it says random and it just says random, right, make sure that you say these things. I want to see those numbers, or I just think you're just memorizing that you need to say N is greater than 30 and you're not actually checking. So make sure these numbers are here. Our N was a T interval. So that was the name of the test that we were using. The actual interval we were doing was 40.751 to 43.249. We're keeping in mind that this is in minutes, right? This is how long it takes. So my conclusion, we are 95% confident that the true mean time to install this hardware is between 40 point, we'll round to 8, so 40.8 minutes, and 43.2 minutes. Bags of a certain brand of tortilla chips claim to have a net weight of 14 ounces. The net weights actually slightly vary from bag to bag and are normally distributed with mean mu. A representative of a consumer advocacy group wishes to see if there's any evidence that the mean weight is not or less than advertised. For this, the representative randomly selects 16 bags of this brand and determines the net weight of each. He finds the sample mean to be X, there should be a bar over that, X bar to be 13.82, and the sample standard deviation to be S equals 0.24. Find the 90% confidence interval for the true mean weight of the bags of tortilla chips. So that means I'm going to be running a panic. Let's do our P. We're trying to find mu, the true mean net weight of the bags of tortilla chips. if you're not sure how to come up with this and you've noticed that this kind of mimics in the conclusion as well, sometimes it kind of helps to look back here. Sometimes they give you hints on what you're really trying to find. So look back at the problem and try to read, what am I truly trying to find here? All right, my assumptions. It did say it was random. So random was stated. N equals 16, which is not greater than 30. But it did say that the population normally distributed. So we're going to say that we're okay. If I had the data actually in front of me, I'd want to plot it and see if that was normal on a histogram. It doesn't give us that, but because it did say the population was normally distributed, and we're assuming this is a random sample, that it should be a normal distribution. So we're gonna say that that's okay. My n should be t interval. This time, since we've done a few of these on the calculator, I want you to go to the calculator and come up with the interval yourself. Pause this video if you need to do that. You should be getting an interval of 13.715 to 13.925. Let's write our conclusion. We are 90% confident that, and then if you've noticed, we're kind of just rewriting what I had up here in my parameter, in my p part. So we are 90% confident that the true mean net weight of the bags of tortilla chips is between 13.7 ounces and 13.9 ounces. So I went back to this. All right, so we've done the panic, we've done the confidence interval for what we think if we were to take every tortilla bag chip or tortilla chip bag, that it would have an average, a true average, somewhere between these two numbers. Now let's look at part B. What do you think of the company's claim that they're 14 ounces? Well, there's a couple things that we could say here. We could say something about it's a small sample, and we should do a larger sample. To be accurate. So that's one thing we could say. But let's look at the actual thing that we got, 13.7 to 13.9. What was the company's claim? That it was 14 ounces. In nowhere, this is not even including 14 ounces. So we're going to say 14 ounces is not in the confidence interval. And we could say that the company may be shortchanging the customer. So if we were doing this test, we may say this, but we need to keep in mind that maybe we should do a larger sample. But if we did a larger sample of 30 or more, and we still got an example like this, we'd say that the company needs to check their stuff to make sure that they're filling their bag or they're being more accurate in their labels. Number 5, for a class project, some students are doing a survey to find out the average number of students ECC students spend studying each week. They take a simple random sample of 91, that's important, so let's say simple random sample, 91 students, and compute a sample mean of 5.4 and a standard deviation of 1.2. Find the 95% confidence interval for the population mean. All right, so I know I'm doing a panic because it's a confidence interval. I know it's a mu, and I know it's t-interval. So these are the kind of things as I'm reading, you should be thinking in your head, okay, then I got to use this, and then I got to use this. So you know what you're doing before you even start. You kind of know what game plan you're going to be running through. Let's start. My p, it's a mean, so my parameter is a mu. Mu is going to be the true, and I'm looking to see what I'm trying to find. I'm trying to find out the average number of hours an ECC student spends studying each week. So we're going to say that mu is the true average, or I can say mean, number of hours. A ECC student spends studying each week. Okay, my assumptions. Random, it does say simple random sample, so let's say SRS stated. Check. And the other one, we're doing means, so it was n is greater than 30. I'm surveying 91 students, so 91 is greater than 30, and that checks off as well. We said before it's a confidence interval, it's a mean, so I'm doing a t interval. Go ahead and pause this video, put these numbers in on your calculator, make sure you're getting the same interval that I am of 5.15 hours and 5.65 hours. Let's do our conclusion. We are 95% confident that the true, and I'm going up here to look up here what it's saying, that the true mean number of hours a ECC student spends studying each week is between 5.15 hours and 5.65 hours. So now, with that same problem as number 5, suppose that the students want to choose a sample size large enough to get a margin of error of 0.10 or less. How do we determine the sample size? And just like before when we did this with proportions, this is going to be a formula. If I wanted to determine the sample size, I want n. And so if I have my E equals T alpha over 2 times S over square root of n, and then I'm going to solve for n. But let's go ahead and plug in the stuff that we do know. My error is 0.10. My T alpha over 2, let's go ahead and do that off to the side. I'm going to be doing an inverse T of my alpha, which is 0.05 over 2, because I'm assuming it's a 95% confidence interval, comma my degrees of freedom, which is 90. Now we're using this because that's what we had up there, and I got negative 1.987. All right, so I got this, and I'm going to plug that in here. Now, whether I got the negative or positive version, it's actually not going to matter because when I find n, I'm going to have to square it anyway. So it doesn't really matter if I put the positive or the negative in there, just like with the other one. My S is 1.2, and over my square root of n. And I'm using the stuff that I had from up above because that's what I have for this sample. So let's go ahead and multiply both sides by square root of n. So both sides by square root of n. This is going to cancel. We're doing some algebra now. So 0.10 square root of n equals 2.384. I could divide by 0.10. And then I'm going to get square root of n equals 23.84. Or if you had plugged in the negative, you would have had a negative here. If I square both sides, I get an n of 568.35. Now, just like before, we need to round up. 568 is not going to be enough because I need that 0.35. So we need to survey 569 students.